Welcome back, engineering students. I am your host, and today I'm putting on my professor hat as we dive deep into the rigorous mathematics and physics of power electronics. Specifically, we're exploring Chapter 2 of our text, AC Transmission Line and Reactive Power Compensation. Now, this title card confronts us with the fundamental engineering challenge of modern power grids. We have dual requirements we absolutely must satisfy. First, we need to transmit as much active power as physically feasible on a line of a specified voltage. And second, we have to control that voltage along the entire line, keeping it within strict limits across incredibly long distances. So let's dive in and see exactly how we solve this. Here's what's on the agenda for today's explainer. We'll start with uncompensated AC line analysis, move on to passive reactive power compensation, compare series versus shunt capacitors, and then get into the modern stuff, active compensation with STATCOM and active compensation with SSC. Let's jump right into Section 1, uncompensated AC line analysis. To really understand how a whole transmission line behaves, we need to analyze this diagram showing voltage and current variation. We're assuming a symmetric three-phase line operating with balanced positive sequence voltages and currents. What we're doing here is looking at a tiny, small element of the line, which we'll call length dx, sitting at a distance x from the receiving end. Look at the variables we're dealing with. Y represents the shunt admittance per unit length, which is made up of conductance G plus JB, the capacitive susceptance. Then we have Z, representing the series impedance per unit length. That's our resistance R plus JX, the inductive reactance. The whole engineering purpose of modeling this small element is to establish our baseline differential equations. As you can see formulated here, the current I at x plus dx equals the current at x plus the current diverted through the shunt admittance, which is y times dx times v. Similarly, the voltage V at x plus dx equals V at x plus the voltage drop across the series impedance, which is Z times dx times I. These physical realities give us the fundamental math we need to move forward. Now, to really analyze this, we need to define two absolutely crucial parameters, the propagation constant and surge impedance loading, or SIL. When we take the derivative of those previous equations, we end up with a second-order differential equation. The solution to that introduces gamma, the propagation constant. Gamma equals the square root of z times y. This little variable dictates exactly how the voltage and current waves propagate and attenuate along the line. Now, for practical engineering simplicity, we usually evaluate what's called a lossless line. We completely neglect series resistance R and shunt conductance G, because honestly, they only have a secondary effect on voltage and power flow. Under this lossless assumption, our propagation constant gamma becomes purely imaginary. It becomes J times omega, our angular frequency, times the square root of L, the line's series inductance, times C, the line's shunt capacitance. The characteristic impedance, ZC, then becomes purely resistive, calculated as the square root of L over C. In this specific lossless state, ZC is what we call the surge impedance, or natural impedance, denoted as Zn. The physical interpretation you need to remember here is that at surge impedance loading, the reactive power generated by the line's capacitance is perfectly, exactly absorbed by the line's inductance. It's a state of perfect balance. So how do we derive the power flow for this lossless, symmetrical line when it's connected to a unity power factor load? We break it down into 4 straightforward steps. Step 1. We assume the sending end voltage, Vs, is held perfectly constant. Step 2. For convenience, we represent the entire line by its Thevenin equivalent at the receiving end. The open circuit Thevenin voltage here is Vs divided by the cosine of theta, where theta is the electrical length of the line. Step 3. This allows us to derive our core power flow equation. P equals the sending voltage squared, divided by Zn times the sine of 2 theta, all multiplied by the sine of 2 delta, where delta is our load angle. And finally, step 4. This brilliant mathematical relationship reveals our theoretical maximum power transfer limit. For a symmetric line, if we take the derivative with respect to delta, we find that the absolute maximum power, Pmax, occurs exactly when the load angle delta hits 45 degrees. But here's where the real-world problems start. Look at this voltage profile right here. The horizontal axis represents the distance along the line, and the vertical axis is the voltage magnitude. Notice the severe, highly problematic voltage variations right at the middle of the line, which we call Vm. When the active power flow P is less than the surge impedance loading, Pn, the line is generating more reactive power than it absorbs. This causes the voltage to physically swell right in the middle, a phenomenon closely related to the Ferranti effect. Now, when P exactly equals Pn, we get that beautiful, perfectly flat voltage profile where Vs equals Vm equals Vr. But when we really push the line hard and P exceeds Pn, the voltage sags dramatically at the midpoint. This physical limitation, this sagging and swelling, is exactly why we must introduce compensation to the grid. Which brings us to Section 2, passive reactive power compensation. So what is the core thesis of passive compensation? Well, as we just saw, a transmission line naturally has series inductance that absorbs reactive power and shunt capacitance that generates reactive power. To counteract these inherent effects, we purposefully install discrete passive components. We utilize series capacitance to effectively cancel out the line's series inductance. This decreases the overall transfer reactance and dramatically increases our active power transfer capability. On the flip side, we use shunt inductance, often called shunt reactors, to absorb that excess reactive power and control that rising no-load voltage profile we just looked at. Let's move on to Section 3, series versus shunt capacitors. Here we're comparing two very distinct topologies side by side. On the left, we have the equivalent circuit of a line with pure series compensation, meaning the capacitor is placed right at the midpoint in series with the line. Notice that with this setup, the midpoint voltage Vm is fundamentally unaffected, but the midpoint current, Im, is modified and increased. Now look at the right. This is the equivalent circuit for a line with a shunt capacitor at the midpoint. The engineering purpose of the shunt capacitor is precisely the opposite. It's designed to support and boost that midpoint voltage Vm, which in turn increases the overall power flow. However, the physical location for shunt compensation is highly, highly sensitive. The midpoint is the absolute optimal placement if you want to maximize power flow. Let's look at the mathematical proof for why we might choose one over the other. Derived from Section 2.5 of our text, we're comparing the reactive power required by both devices to achieve the exact same amount of maximum power transfer. If we set the maximum power flow equations equal for both cases, we derive a truly fascinating relationship. The reactive power supplied by the series capacitor divided by the reactive power supplied by the shunt capacitor is exactly equal to the tangent squared of delta max, divided by 2. Since the maximum operating angle, delta max, is typically kept well below 90 degrees in the real world, this tangent squared fraction ends up being significantly less than 1. What does that mean? It mathematically proves that a series capacitor requires a much, much smaller reactive power rating to achieve the exact same increase in power transfer. Put simply, the series capacitor is significantly more effective at pushing power than the shunt capacitor. But it's not all good news for series capacitors. Check out these equivalent circuits for determining the electrical resonance frequencies of these compensated lines. For the series capacitor, the resonance frequency equals the operating frequency, F0, multiplied by the square root of 1 minus the degree of series compensation, KSE. Because KSE is a fraction, this resonance frequency is literally always less than the operating frequency. This introduces a critical danger, sub-synchronous resonance, or SSR. These subsynchronous frequency currents can interact destructively with the mechanical torsional modes of generator turbines. We're talking about catastrophic shaft failures. Because of this severe risk, series capacitors require incredibly expensive overvoltage protections during fault transients. In stark contrast, the shunt capacitor's resonance frequency is supersynchronous, meaning it's greater than F0. It completely avoids the dangers of SSR, making it structurally much safer. That brings us into the modern era with Section 4, active compensation with STATCOM. Take a look at this equivalent circuit featuring a STATCOM sitting right at the midpoint. A STATCOM, or Static Synchronous Compensator, operates fundamentally differently from a passive capacitor. Assuming losses are neglected, a shunt-connected STATCOM draws a pure reactive current, IR. The absolute engineering brilliance here is that it acts as a constant reactive current source. Think about a passive shunt capacitor. Its reactive power output drops quadratically as line voltage drops, right when you need it most. But a STATCOM dynamically regulates its reactive current independently of the bus voltage. This makes it dramatically more effective at supporting the grid during severe low-voltage emergencies. This power angle curve really illustrates the STATCOM's impact. The lower curve charts the baseline power flow, where the injected reactive current, IR, is 0. The upper curve charts the system when it's dynamically injecting a capacitive reactive current. Specifically, IR equals negative 0.5 per unit. Not only does this dynamic injection shift the maximum theoretical power peak significantly higher, but it fundamentally alters the physics of the line itself. The angle at which maximum power occurs is no longer hard-capped at 90 degrees. It is physically extended past 90 degrees, opening up an entirely new, stable operating margin for the power grid. It's a real game changer.
And finally, Section 5, Active Compensation with SSSC.
Tracing this circuit diagram, we have an SSC, a Static Synchronous Series Compensator, positioned at the midpoint of the line. Now, unlike the STATCOM, which is shunt-connected and injects reactive current, the SSC is series-connected. It utilizes a voltage source converter to inject a pure reactive voltage directly in series with the transmission line. The equations shown here reveal a massive advantage to this approach. The increase in active power transfer is directly and linearly proportional to the reactive voltage injected by the SSC. This gives operators incredibly precise dynamic flow control. Let's analytically compare the required ratings for these two active devices if we want to achieve the exact same level of active power enhancement. Going back to the math from our lecture notes, we can prove that the required rating of the SSEC equals the tangent squared of delta max divided by 2 multiplied by the rating of the STATCOM. Again, because delta max is generally small, this conclusively proves that a series-connected SSEC requires a significantly smaller MVA rating than a shunt-connected STATCOM to push the exact same amount of extra megawatts down the line. It is just an incredibly efficient use of power electronics. Okay, let's summarize our core engineering takeaways for today. First, uncompensated AC lines are physically limited by severe midpoint voltage variations under varying loads. Second, passive series capacitors are highly effective at boosting power transfer, but they carry the very dangerous risk of subsynchronous resonance. Third, passive shunt reactors are absolutely necessary to control the no-load Ferranti effect. Fourth, modern STATCOMs dynamically and actively regulate voltage by injecting independent reactive current. And fifth, SSSCs actively enhance power transfer efficiently via series reactive voltage injection. Before we wrap up this explainer, I want to leave you with a provocative engineering question. Throughout this masterclass, we've derived all these equations assuming steady, synchronous generators driving the grid. But as we transition to a frankly chaotic grid dominated by highly variable inverter-based renewable energy, like wind and solar, that traditional inertia just vanishes. So how must these fundamental AC line equations and these advanced FACS devices adapt to secure the real-world grids of tomorrow? That is the massive challenge awaiting you out there in the field. Thank you for joining me today. Keep analyzing, keep calculating, and I'll see you in the next one.